Yeah, also at any point of time, feel free to interrupt me if you have any questions or anything. It's fine if you interrupt. It's a tutorial session. So this matrix can be given by this 4 by 4 matrix. So you saw a single qubit. Single qubit has a 2 by 2 matrix, a complex matrix. Two qubits have 4 by 4. That is 2 power 2 times 2 power 2 dimensional matrix, because we have two basis states for each qubit. So this you can obtain by just expanding this state. So here, uh, this 0, comma 0 is a projector, and we can just directly substitute the uh, vectors. So 0 is the 1, 0 vector. This thing is a transpose conjugate, the dual. I write this as this. So we multiply this element twice and get 1, 0, 0, 0. So why I say this is a projector is if I have 1, 0, 0, and if I have the state, say alpha, beta, what this gives me when I apply this operator on the state, this state, I just get alpha 0. It projects it to this state. So note that this is not a normalized wave function, and so it projects it to the space. So this together is a reversible normalized. It's a operator. It's a valid operator, valid quantum operator. But this separately is just a projector operator. Anyways, so now you have the state 0, 0, ket 0, bra 0 as this matrix, and now you tensor product this with the INT operator. So INT operator is 1, 0, 0, 1. So if we expand this, what you get is so 1 times the INT operator, 0, sorry, not plus, apologies. Similarly, you get, this is how you do a tensor product. If you're not, so this is how you do a tensor product. So these elements go to 0, all of these elements, the 4 elements. So effectively, what we'll end up with is 1, 0, 0, 1, and all these will be zeros. Similarly, when you evaluate this part, what you obtain is you get 0, 0, 0, 0, 0, 0, 1, 1 in over here. You can try doing it by yourself. So when you add both of this plus the matrix above, you get the C0 gate. So that's how you get this matrix form and effectively go from this to this. So now the task I've given over here in the first part is to show that the swap gate is basically 3 C0s. So before we start this, a swap gate is basically which swaps the states. So if the state is 0, 1, a swap gate makes it 1, 0. Similarly, if it's 1, 0, it swaps it to 0, 1. But if you see the state 0, 0 is still the state 0, 0. It doesn't change anything. The state 1, 1 doesn't change anything again. So you can see that this matrix, the 4 by 4 matrix, this element can be in a way obtained by taking the operator, say if the operator is some A operator, and I find the element at this position by taking the, the expectation of this operator at this particular state. It's like I'm finding the matrix element, and so on so again. So similarly, using these things, you can directly, instead of evaluating the entire thing, you can directly show that this swap gate is of this form and 0 everywhere, 0 everywhere. So the task over here is to show that this equality holds. So you can just directly multiply this. There'll be 4 matrices to multiply. This times and with this matrix, which is basically C naught of BA. So C naught of AB is not the same as C naught of BA. So let's see what C naught of BA is. We will get rather X. So the operator is given in the operator form. We have I times tensor product of 0 plus X tensor product with 1. So if I expand this, I get this as of the form 1, 1, 0, 0, and zeros everywhere. The 4 by 4 matrix. And I get, if I expand this, I again get 0, 0 here, and I get oh sorry, I made a small mistake. So let's just write the whole thing. Get 1, 0, 0, tensor product with 1, 0, 0, 0 plus 0, 1, 1, 0 tensor product with 0, 0, 0, 1. So if I do the multiplication, what I get is I get 1, 0, 1, 0, and zeros everywhere, plus zeros over here. I get zeros over here also. And I get, sorry, get zeros over here. I get 0, 0, 0, 1. I get 0, 0, 0, 1 here. I get full zeros here. So if I add this, what I get is the form which I get is 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. So this is the flip version of C naught. That is C naught B, BA. So adding this here, I get, so if I multiply these three matrices, I should get my swap gate. My swap gate matrix is this one. So this is basic matrix multiplication, and you can try it for yourself. So effectively what it's saying is the swap gate, which is represented in a circuit as the following diagram. Basically two X's and a line connecting them. This is equivalent to 3 C naughts. Okay, so hold on to this thought and let's proceed to the next thing. So part B, I think it is little obvious, so I'm not going to do that. I'm going to skip that. Part C. So a CZ operator basically applies a phase of -1 when both the states are 1. Effectively, it's like control not, except it's a control Z operator. It applies a Z operator. So there are two parts to this thing. One is show that Z of AB is same as Z of BA, and also Z of AB equal to Z of BA, which is also equal to H INT times Hadamard times C naught AB times INT times Hadamard. Effectively, what this is saying is this circuit. Usually, we represent CZ just by two dots over here because of this property. So there's no directionality in this. So what it is saying is have a Z operator is equivalent to Z operator is equivalent to C naught and 2 Hadamards. So this, instead of doing the matrix multiplication, let's use the bracket notation to make our life easier. So C naught of AB is basically 0 INT plus 1 times X. When we apply Hadamard's on the second qubit, so effectively what's happening is there's only identity matrix on all the first qubits, so that this doesn't change. So applying Hadamard's on the identity, say I get 0, 0, because identity, nothing happens over here. Let me rewrite that. I times I tensor product with HP times I dot HP. Basically, I'm multiplying by HP, I tensor product with HP on both sides. So this one plus I times one projector times HP dot X. So effectively, this doesn't change. This doesn't change. And if you observe this, basically this is HP times I times HP. This is basically HB squared. And if you know Hadamard gate, it's basically 1 1 1 minus 1 times root 2. If I multiply this twice, basically I get the INT matrix. So as Rohit had mentioned in his lecture. So this gets 1 2 0 0 2, and this becomes INT. So this is just INT matrix. So this is 0 0, and this becomes still the INT matrix. And this is again 1 1. And now consider this part. So this one, I get HXH. But HX is basically Z operator. So this you can again show by just calculating it. 1 1 1 minus 1, 0 1 1 0, 1 1 1 minus 1 times 1 by 2, because 1 by root 2 twice. So if I calculate this, I basically end up with 1 0 0 minus 1, and which is the Z operator. So effectively what I've done is the product I've shown there is equal to 0 0 times identity plus 1 1 ket 1 bra 1 times Z. Effectively, this is a CZ operator going from A to B. To show that CZ of AB is CZ of BA, we can just expand both of these. So I can write 0 0 1 1 times 0. So what I've done here is I've written my identity element as projected to 0 state and projected to 1 state, because identity is basically 1 0 0 1. So these elements. I hope this is clear. So once I write this like this, I can just shuffle the terms, and I can reduce it to of the form. So I group these two terms. So that will give me and if I say group these two terms, this now gives me 0 0 minus 1 1 times 1 get 1 bra 1. So this is basically identity times 0 0 projector plus Z times 1 1 projector. So effectively, I've shown that CZ can be applied in either ways. So let's move to the last part. So basically, now is the main part where we try to show that the teleportation protocol is same as just a swap gate between the initial qubit and the final qubit. So let's just redraw the circuit. So if you see that in the problem set, these double lines are there. So these double lines basically represent classical bits rather than quantum bits. Single line is a quantum channel, a quantum bit traversing through time. And sorry, there's a Hadamard also here. So I start with the state 0, 0. And this part makes a bell state. So I have a bell state over here, which is usually represented as with 5. 5 plus over here because I get the state over here as 0, 0 plus 1, 1 by root 2. Then I do this. Then I do the following operation where I apply C naught and a Hadamard, and then I measure these and send my measurement values to Bob. This is Alice and this is Bob. This is basically the quantum teleportation protocol which was discussed in the lectures. So now let's try to reduce this to a swap gate. So first, notice that this control gate is basically a measurement gate followed by classical application of a NOT gate. But this is in a way similar to just directly say first applying a NOT gate and then measuring it. So you can think of if I measure state 0 here, the NOT gate won't be applied. Similarly, if the state was 0 over here, it won't be applied. And if the state was 1, here the gate will be applied. If the state was 1 over here, it will be applied and then it was measured. So it doesn't make a difference. So this is the first mapping we do. Similarly, we can also translate this, the Z gate, control classical Z gate. So this is equivalent to my Z gate. So if I replace this in both of these positions, let's see what happens. Um, so now what happens is I replace this with a C NOT gate. And this becomes a measurement over here. Now I replace this with a CZ gate from here to here. So now we have also shown that CZ of AB is equal to CZ of BA. So this allows us to flip this. So we can thus write this as CZ over here. But this does a Hadamard here. So I can add and since I have Hadamard times Hadamard is my identity operator, I can just add two Hadamards over here, this place. So effectively, can I add a Hadamard here, and this thing becomes a NOT gate, as we had seen in the second part. It becomes a C NOT gate here now. So effectively, this reduces to the Hadamard here, NOT gate here, NOT gate here, and there's a C NOT gate from here to here, and there's a Hadamard and measurements. So now now one more thing. So we saw that the state 0, when the state 0 Hadamard is applied, this becomes the plus state. And the plus state, if I apply a NOT gate on the plus state, this is the same as the plus state because I have state 0 plus state 1 by root 2. I apply the NOT gate. This becomes state 1 plus 0 by root 2, which is basically my plus state, which doesn't change anything. So what I do is I add a NOT gate from here to here. Let me explain why. So I add a NOT gate from here to here because this state is still a plus state and plus state doesn't change if a C0 is added or not. So hence I add this this gate here. Here, what you need to, another thing to show is, which you can try later, this gate, this set of gates, is basically equivalent to my C0 from here to here. So this is a little non-trivial result, which you can try showing later by multiplying again. It is like in the next question, the fourth question, where we try to show it's something like that, but not the same. So effectively, we use this identity over here and then we reduce this gate system to a C0 between the first qubit and the third qubit. So effectively, now what the circuit becomes is, I have a Hadamard here, I have a C0 from here to here because of this. And earlier I had a C0 from last qubit to the first qubit. But now, remember that we started with the state 0 here, and we started with the state psi over here, which is the target state which needs to be sent. Any control gate controlled on the state 0 doesn't make any difference. So it don't make any difference if I add a gate over here. So this is a redundant gate. So this redundancy, I'm just adding it for my convenience. So, but notice that these three gates are now a swap gate. And thus, this is equivalent to effectively swapping these gates. So the non-trivial part of this question was this reduction, which I request you try it out by yourself. And this addition of my C0 gate over here, and this addition of C0 gate, because C0 on an X gate doesn't change anything. So I hope everyone was able to follow them.
Praveen, what about the Hadamard gate in the circuit above?
What?
There was a Hadamard gate in the circuit above, right?
Which bar?
In the first, on the first qubit at the end, just before the measurement.
It doesn't matter. It's anyway swapping it. And so the swap gate over here. So we end up with, just 1 second.
Yeah, sure.
Yeah, sorry for letting you guys inside late. I didn't see the invite. So, anyways, so here I have a Hadamard gate and then a measurement, right? So anyway, the state is psi here and state 0, and the Hadamard over here also. So the state over here will end up with plus state, and over here I end up with the state 0. I end up with the state psi. So they're not entangled. So this Hadamard will just make the state to a plus state, and which will be measured. And similarly over here also it will be measured, and the state will just be psi. So effectively, your state psi over here has been has been like teleported to my last qubit by the socket.
Yeah, right. Thank you.
Any questions? Okay, if no questions, we proceed then. Uh, Priya, can you continue?
Yeah, yeah, sure. I'll just, are you able to see it?
Yes.
Okay. So I'll be using slides to discuss the problems 4 and 6. The fourth problem was basically about implementation of CPAR and NOT gates using Toffoli gates. So as we saw in the lecture, the Toffoli gate is also called as this is C square NOT gate. So it's also called as a C square NOT gate or the CC NOT gate. And the Toffoli gate is similar to the C NOT gate, but here there are multiple control qubits and one target qubit. So only when all the control qubits are in the state one, then only the C NOT, the NOT gate or the X gate is applied on the target qubit. So it is known that the Toffoli gate along with the Hadamard gate is universal for quantum computation when certain quantum states can be synthesized. And it's also known that the CNOT gate along with a single qubit gate that is H, S, and T, they form a universal set for quantum computation. So in this particular question, what we are trying to do is we're trying to illustrate the construction of CN NOT gate using Toffoli gates. So in the first problem, the problem 4A, the A part, basically the question is to show that the C NOT gate, that is n equals to 1 in the C power n NOT gate, can be constructed using one Toffoli gate. So how do we go about solving this problem? So as we learned in the lecture, in the C NOT gate, what the C NOT gate does is it performs X on the target qubit if the control qubit is in state 1, else it performs an identity operation. In the Toffoli gate or the C square NOT gate, it performs X on the target qubit if both control qubits are in state 1, else it performs an identity operation. Now, for the C NOT gate, we just need one control qubit. We do not need two. And in the Toffoli gate, only if both the qubits are in state 1, then only the X operation is performed. So what we do is that we just set one of the control qubits of the Toffoli gate to 1, and this way we get a C NOT gate. So this is the Toffoli gate. We just set the one of the control qubits to 1, and we get a C NOT gate. So these two are equivalent forms. So hence from the Toffoli gate, we can get the C NOT gate. Okay, so that was problem 4A. Do any of you have any doubts?
Clear.
Okay, fine, thanks. Yeah, the next problem is about the C square NOT gate. So let's learn about how the C square NOT gates acts on different states. So here the question says, which states do we obtain on applying the C square NOT gates, that is the Toffoli gate, on the states plus 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 and plus plus minus. So here we are considering the first two qubits to be the control qubits and the last qubit to be the target qubit of the Toffoli gate. So just a brief recall from the lecture that the way the C square NOT gate acts on the basis states. So here the C square NOT gates only acts non-trivially on 110 and 111 because the first two qubits of only these two states are both in the state 1. So only here it's flipping 0 to 1 of the last qubit and 1 to 0. All the rest of the states remain the same. So let's remember this as we move on. So let's first consider the second state over here, that is plus plus minus. And let's expand this. So we know that plus can be written as 0 plus 1 by root 2, and minus can be written as 0 minus 1 by root 2. So next, let's multiply all of this together. So using the representation as we learned in the lecture, we get 0, 0, 0, and then we have a negative sign coming in for 0, 0, 1. And similarly, we can get all the terms, and we get the negative sign similarly everywhere. So we get 0, 0, 0, minus 0, 0, 1, and then plus 0, 1, 0, minus 0, 1, 1, and 1, 0, 0, plus 1 minus 1, 0, 1, and 1, 1, 0 minus 1, 1, 1. And this is how we get the superposition over here. And by multiplying all the denominators, we get 2 root 2. So let's bring this common factor outside, and because the Toffoli gate is a linear gate, we can apply it on each of the basis states. So that's what we do over here. We're just applying it on each of the basis states. And as we saw in the previous slide, the Toffoli gate only changes the last two basis states, and it does not change the rest. So all the rest of the states remain the same, but only the last two states, here it's flipped. The last qubit is flipped. So 110 becomes 111, and 111 becomes 110. Okay, so this was the state which we obtained in the previous slide. So now what we'll do is we'll just look at two states at a time. So let's look at these two states. We see that 0, 0 is common, so we can just pull out the common state, and we are left with 0 minus 1 by root 2. Similarly, when we look at these two states, we have 0, 1, and we are left with 0 minus 1 by root 2 again. And similarly here it's 1, 0 is common, and again we have 0 minus 1 by root 2, and even in the final one we have 1, 1 being common, minus get 1, 1 being common, and we are left with 0 minus 1 by root 2. So we can replace this 0 minus 1 by root 2 everywhere with a minus state. So that's what we have done here. We have 0, 0 minus plus 0, 1 minus plus 1, 0 minus minus 1, 1 minus. So now we have the state. Can we reduce it further? So we can look at these two states together. You see that the first and the last qubits are in the same states. So when we kind of take out the common states, we are left with 0 plus 1 by root 2. Similarly, here the first and the last qubits are in the same state. So we get 0 minus 1 by root 2. And this is nothing but the plus state, and this is nothing but the minus state. So finally, we get 1 by root 2 into 0 plus minus plus 1 minus minus. So we get a superposition of this. And so when we apply the Toffoli gate on plus plus minus, we get the superposition, which is an entangled state over here. Similarly, using very similar techniques, we can show that when we apply the Toffoli gate on plus plus plus, it remains to be plus plus plus. And one way to look at it, why this is the case, is because the final state is in the state plus, and because plus is a plus one eigenstate of the X operator. That is nothing but an eigenstate of the X operator with eigenvalue 1. It does not, applying X operator on plus state does not change it. So therefore, it remains the same. And here, this is one of the examples of a stabilizer of a state. So the Toffoli gate is a stabilizer of the plus 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 state. Yeah. Is this question clear? Do you have any doubts? Okay, fine. I'll move to the next question then. So in the next question, we'll see how do we implement any CPAR and NOT gate using Toffoli gates. So the question is, show that the CPAR and NOT gate can be constructed where n is greater than 1. How many Toffoli gates in terms of n are required for the construction of CPAR and NOT gate using Toffoli gates? So CPAR and NOT gate is similar to Toffoli gate, but in Toffoli gate we had 2 control qubits. Here we'll have n control qubits, and we have 1 target qubit as usual. So only if all the control qubits are in state 1, then we apply the bit flip operator on the target qubit. So mathematically, we can represent it in the following form. So we can, so when the 2-qubit state, like for the Toffoli gate, um, when the two control qubits are in state 1 1, then an X operator is applied. Else, for the rest of the states, here we are represented by I minus 1 1, ket 1 1, bra 1 1, because I is equal to the summation of all of these projectors of 2-qubit states. So when the first two, that is the control qubits, are in state 1 1, then the X operator is applied. Else else nothing is performed. Similarly, for the C cube NOT gate, we have a similar relation, and even for C power n NOT gate, we can represent it similarly, but just increasing the number of ones over here. So we can kind of show the relations using these mathematical expression over here, but it they're a bit more complicated. So let's look at it graphically. So first, let's see what happens when a Toffoli gate is applied to the basis states, because as we know that all the unitary operators, and especially Toffoli gate is also a unitary operator. So when we apply a unitary operator on a superposition, it's equivalent to applying the operators and then taking the superposition. So let's just look at the basis states. So when the Toffoli gate is applied on the basis states, let's say A, B, and C, then A and B do not change, they remain in the same state. But for C, we are only if A and B are in state 1, we are going to flip the gate. So here, this is equivalent to C plus A into B. So where plus is the XOR operation and dot is the AND operation. Similarly, when we consider C power n NOT gates, and again we consider basis state C1, C2, and so on till Cn for n control qubits, and the state T for target qubits, the first n states remain the same, while the final state becomes T plus C1 into C2 into Cn, where here it's basically the AND operation again, and this is the XOR operation. So this is the solution of how to construct C cube NOT gate from Toffoli gate. Like, how is this a solution? I'll be explaining it in the next slide. So here, basically, we need 3 C NOT gates in this fashion, where A, B, and C are the control qubits, and D is the target qubit. And the 0 state is an ancillary state. So we have a register, and we're just getting a 0 state from that and using it over here. And actually, we can see that these two C NOT gates would be sufficient, but we are even using this particular C NOT gate so that we can revert back this 0 back to the 0 state, so that it can be used again for any other operation. And yeah, so let's see how exactly is this circuit equivalent to a C cube NOT gate. Yeah, so we prove it by showing that when this particular circuit is applied on these inputs, D is transformed from D plus A into B into, D is transformed to D plus A into B into C, and A, B, C remain the same. So let's have a look at it. So this is the initial circuit where we're just, this is the first step in the circuit where we're applying just one C naught Toffoli gate. So here this remains A, this remains B. This will become 0 plus A into B, which is nothing but A into B. So now let's apply the next C naught gate. So when we apply the next C naught gate, here it was AB, so this remains the same. This remains the same, which is C, and here it will be D plus A into B into C. So now we have actually already got A, B, C, and D plus A into B into C, which is what the Toffoli gate should do. But we see that this the third qubit, which is basically the ancillary qubit, it is in the state A into 0, and we want to revert it back to zeros so that we can use it for any other such operations. So for that, we use one more Toffoli gate over here, and this will become A into B plus A into B, so it reverts back to 0. So therefore, this is equivalent to just using one C cube NOT gate. So using 3 Toffoli gates, we are able to get one C cube NOT gate. Similarly, it can be proved that for C power n NOT gates, we can have a very similar circuit. I mean, a circuit which follows similar structure, and using multiple such ancillary qubits, we can obtain this particular circuit, and this is equivalent to CPAR and NOT gate. So now let's count the number of Toffoli gates which are required. So here we can see that for the first 2 qubits, we need one one Toffoli gate, and then on for every qubit that we add to the as a control, we need one Toffoli gate. Two. We need one on this end and other on this end. So for the first 2, we need these 2, and then every time we add one control qubit, we need 2 Toffoli gates. And for the last control qubit, we just need one Toffoli gate so that we apply it on the target. So the total number of Toffoli gates required is 2 plus 2 into n minus 3 plus 1, which is equal to 2n minus 3. So for n greater than 2, the CPAR and NOT gate requires 2n minus 3 Toffoli gates. Yeah, so do any of you have any doubts in this problem?
It is clear.
Okay, fine. Let's proceed.
Just a minute. Could
Yeah,
you
sure.
go back?
Okay.
So for when you say CPAR and not, N doesn't include the target, right?
No, it doesn't include the target.
So when you're calculating the number of gates, the last slide of this question, is it N minus 2 or N minus 3 for the second term? Hello?
Yeah, I'm just thinking about it. So I think it's n minus 3 because here we are considering this and this control, and we are considering this control. So we are removing 3 of them. So in
Okay.
middle it
Yeah.
should be n minus 3
Okay, sure. Thank you.
because this last one Toffoli gate is for this control qubit Cn,
Okay.
and this 2 is for the first two
Okay,
together.
sure.
Yeah. Okay. Yeah. One way to kind of verify is maybe just substitute n equals to 2, and you'll get 4 minus 3, which is 1. So the Toffoli gate is a C² NOT gate, right? So we can
Yes.
just substitute n equal to 2 and we get the answer. Yeah. Any other doubts? Okay, then let's proceed further. So the next question is based on measurement-based quantum computation. So all of us are aware of the circuit-based quantum computation, where we have the inputs and then we are applying gates on this, and then we obtain the outputs, and that's how we perform quantum computation. But there's one more way of performing quantum computation, and that's called the measurement-based quantum computation. So measurement-based quantum computation involves performing quantum operations on qubits by applying a sequence of measurements to a particular entangled state using a designated measurement basis. And this form of quantum computation is also universal, and that is what we'll be showing through this particular problem. So as we saw in the lecture, the single qubit gates, all single qubit gates, along with the CNOT gate, form a universal set for quantum computation. So that's what we'll be showing in this lecture. In this problem, that we can implement all the single qubit gates using measurement-based quantum computation and also the CNOT gate. Okay, so the first part of the problem is on the post-measurement state. So there was one typo in the question. So here the question is, what are the post-measurement states obtained when the first qubit of the states, psi naught equals to 00 plus 1 by root 2 and psi 1 equals to 1 by root 2 00 plus half 01 minus half 11 are measured in the x basis, plus minus basis, and the z basis, which is the 01 basis respectively. So here the measurement, we are just performing it on the first qubit, and we are seeing what happens to the entire state. We know that the first qubit collapses, but let's also see what happens to the second qubit. Does it collapse, or which state does it go into? So here this was the measurement postulate which was there, which is a quantum mechanics postulate. So here it basically says that if we are using a collection of measurement operators mm, then the probability that the result m occurs is given by p of m equals to psi mm dagger mm psi, and the state after measurement is mm psi root of p of m. So let's apply this postulate and see how do we get it. So what we are doing is we are just using projective measurements. So all our measurement operators are of the form, suppose if we consider an orthonormal basis B1, B2, it can be either plus minus basis or 0, 1 basis or any orthonormal basis. Let's look at it from a general point of view. So if we consider the basis to be B1 and B2, then the first measurement operator will be the projection operator B1, B1, and the second measurement operator is the second projection, which is B2, B2, based on the two bases. So these two measurement operators project the state onto the state B1 and B2. Here, even in D2 correspond to the corresponding eigenvalues with respect to the measurement basis states. So for now, like we saw through the lectures, that the eigenvalues are usually plus and minus 1 for 0 and 1 for the x and z operator. So let's set E1 to 1 and E2 to minus 1. Then we have M1 is B1 B1 and M minus 1 is B2 B2. So now using the formula which we obtained, which we saw before, we get P1 is equal to psi M1 dagger M1 psi, which is equal to psi the projector B1 ket B1 bra B1 dagger ket B1 bra B1 psi. So here when we apply the Hermitian conjugate, we get back the same thing because it's a projection operator. So here we see that B1 and B1, their inner product is 1. So therefore we get it in the following form over here. And again, as I mentioned, the inner product of any state with itself is 1 because every state is normalized. So we get this to be equal to in the inner product of psi and B1 into the inner product of B1 and psi, which is nothing but the modulo square of the inner product of B1 and psi. So similarly, using very similarly, we can get that the probability of getting minus 1 as the eigenvalue, or basically the post measurement state as B2, is mod of B2 into the inner product of B2 into psi the whole square. So what about the post measurement state? So again, we use the formula which I showed before, and we again the measurement operator is basically the projection operator. We apply the projector, and here we get the inner product B1 into psi, and the final state is basically B1 itself, because we know that the post measurement state is basically one of the basis states. But here we have this factor, so again we can replace whatever we got in the previous slide with the value of P1, and we get that to be mod of B1 inner product of B1 and psi whole square, and this is basically a phase factor. So therefore, this is nothing but equal to B1 up to a global phase. So this was for one qubit measurement. So similarly, even for m equals to 1, that is for the other measurement basis, other basis, we can show that the state of the measurement is nothing but B2 up to a global phase. So this is for one qubit. Let's see what happens when we consider two qubits. So when we consider a 2-qubit system and perform measurement only on one qubit, we obtain the probability and post measurement states using similar relations as before, but we'll have to apply the identity operator on the second qubit because we are not measuring that particular qubit. So here, instead of just the projection operator, we take the projection operator tensored with identity, and similarly, even while computing the post measurement state, we consider that. So now let's see what happens next. So let's look at the first problem first, where we are considering the plus minus basis states, and we are considering psi equals to the Bell state. So here B1 equals to plus, B2 equals to minus, and psi equals to 0, 0 plus 1, 1 by root 2. So let's first compute the probability of obtaining 1 as the outcome, the eigenvalue 1 as the outcome. So here we're going to substitute, sorry, here. Yeah, so in this particular equation, we're going to substitute psi with the Bell state. We take the dagger of it. Then we have the projection operator tensored with the identity. And then we have the Bell state again. So the Hermitian conjugate of the Bell state is basically obtained as bra 00 plus bra 11 by root 2, and the rest remains the same. Then we can perform the multiplications here. So here, we have, because of the identity operator, the second qubit gets multiplied directly with the second qubit here, and the first qubit gets multiplied with, so it will become 0 into plus into 0 into, sorry, into plus into 0, tensored with 0 into 0 directly. And similarly, we get 4 such terms, and we know that the inner product of 0 1 1 with 0 is 0. So these two terms just go to 0. We are just left with these two terms, and we get 1 and 1, sorry, half and half over here, and finally we get the total probability to be half. So similarly, we can also show that p of -1 equals to half. Okay, so, and the next, using the relation in the previous slide, we get the post measurement state also very similarly. So we apply the projection operator tensored with the identity operator on psi, and we divide it by root of p of 1. Root of p of 1 was 1 by root 2. And when we apply this projection operator tensored with the I on the Bell state, we get plus plus into 0 over here, tensored with the second qubit in 0, plus 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 into 1 over here, tensored with 1. So this is nothing but, we know when a projection of plus is taken on the state 0, it gives us 1 by root 2. And when a projection of plus is taken on the state 1, we get plus 1 by root 2 again. So that's why we are getting 1 by root 2 plus over here. This is tensored with 0 plus 1. And hence, we can write this as plus and plus, because 0 plus 1 by root 2 is plus. So therefore, the post measurement state in the first case, that is for m equals to 1, is plus plus. Similarly, we can show that when m equals to -1, the post measurement state is minus minus. Okay, so this was for the first state. Now let's look at the second state. So for the second state, we have 1 by root 2 0 0 plus 1 by 2 0 1 minus 1 by 2 1 1. So let's rewrite this. So for this state, we have psi 1, this we can rewrite as 1 by root 2 into 0 into 0 plus 1 by root 2. And here it is minus half into 1 1. So I've just written it in this form because in the measurement operator, we are considering this projection operator, and the basis there is in the next slide is 0 0. So because we know that 0 and 1 are orthogonal, writing it in this form would just cancel out the second term when we are measuring the first term. So hence we, using this particular formula, we get p of 1 equals to half into 3 by 2, which is nothing but 3 by 4. And we get p of 1 equals to 1 by 4. So basically half, yeah. So next for the post measurement state. So similarly, using the formulas before, when we use the formulas directly, we, as I mentioned, the second in psi 1, the second part has 1 over here, and because this has a projection of 0, the second part nullifies, and we are just retained, we just obtained the first part, and this is what we get with a normalization factor. So hence, when the outcome is 0, this is the post measurement state, that is the first qubit is in 0, and the second qubit goes into a state root 2 by root 3 0 plus 1 by root 3 1. And the post measurement state, when the measurement outcome is -1, that is the post measurement state is 1, and we get the second qubit to be in the state minus of 1. Yeah, so so we have obtained the post measurement states for both the states when measured in the x and z basis. So do you have any doubts in this part? Okay, then let's go to the next question. Okay, so the next question is about looking at what happens when the control Z gate is applied on the plus plus state. So why we are considering the plus plus state? Because we'll see it in the next question. Basically, in measurement-based quantum computing, other than the input states considered, the other qubits are initially set to the plus plus state, and then we'll be applying CZ operations on it. So in measurement-based quantum computation, what happens is we have the plus states, we have the CZ operations, and then we have measurements performed on these particular entangled states, which are obtained after performing CZ operations on the plus plus states. So here we consider two qubits initially in state plus operated upon by a control Z operation. We need to find what is the final state of the qubits. Is the final state of the qubits an entangled state? So let's again recall what is the CZ operation. So when the CZ operation acts on 0, 0, it remains to be 0, 0. When it acts on 0, 1, it does not change the state. Again, for 1, 0, it does not change the state. But only when it's 1, 1, then we get a phase shift, phase flip here. That is, we get a negative sign over here. So now let's apply it on the plus plus operator and see. So the plus plus operator, we can expand it out as 0, 0 plus 0, 1 plus 1, 1 plus 1, 0 by 2. And as CZ is linear, we can apply CZ on each of these basis states. So CZ applied on 0, 0 will give us 0, 0. CZ applied on 0, 1 will give us 0, 1. CZ applied on 1, 0 will give us 1, 0. And CZ applied on 1, 1 gives a minus 1, 1 over here. So now again, taking the common factors over here, let's look at these two together first. So we just take the 0 out. We are left by 0 plus 1 by root 2. That is a plus over here. And again, here we take 1 out, and we're left with 0 minus 1 by root 2, which is a minus operator over here. So therefore, we get the state in this particular form. And as we can see, this is an entangled state, because we cannot represent the state of the first qubit independently of the state of the second qubit. So yes, the final state is an entangled state. So we'll be using this relation in the next problem. Do you have any doubts in this question? Okay, let's proceed further. So the next problem, in this particular problem, what we are going to show is that single qubit gates can be implemented through measurement-based quantum computation. So let's initially consider two qubits, with the first qubit initially in state psi equals to A0 plus B1, and the second qubit initially in state plus. We apply a controlled control Z operation, which is a CZ operation on the two qubits. So we need to find what is the first part of the question is to find what is the final state of the qubit when we apply a CZ operation on psi and plus. So let's first do that. So when we apply a CZ operation on psi and plus, we obtain, so let's expand out psi. Psi is nothing but A0 plus B1. And let's expand it out further. We get, get A0 plus B1 plus. And when we apply CZ on this, because the first qubit is in state 0, it doesn't do anything on the second qubit, but here as the first qubit is in state 1, it applies a Z operation. And we know that when Z acts on plus, we get a minus state. So that's why we get A0 plus B1 minus. Okay, so the next part of the question is about show that when the first qubit of zeta is measured in the basis, in this particular basis, the second qubit transforms to a state x bar s u theta l, where s belongs to 0, 1 is the measurement outcome. So here it can be 1 and minus 1, but I'm just I've represented it as 0 and 1, where 0 corresponds to eigenvalue 1 and 1 corresponds to eigenvalue minus 1. And here u theta l equals to 1 by root 2, 1 e power minus theta, 1 minus e power minus theta. So we compute the post measurement state similar to the previous problem, but here we are similar to the part A of this question. But here, let's not look at the denominator, that is root of p of 1, because we know all quantum states are normalized. So we can just normalize it at the end, because we are, however, dealing with unitary operations here. So let's, so we basically take the projection operator onto a particular basis. So let's first look at the post-measurement state when the measurement outcome is 1, where basically it corresponds to s equals to 0 over here. So here we are taking the projector, we are tensoring it with the identity operator, and we are applying it on zeta. So we obtain zeta to be equal to a0 plus b1 minus. And when we apply this projection operator, what happens is that this projection operator only acts on the first qubit. So we get a theta naught plus the inner product of theta naught with 0 tensored with plus b theta naught, the inner product of theta naught with 1 tensor product with the minus state. So here we can see that the theta naught state is basically is common to both the terms. So we can just take it out. We take the tensor product into a theta naught 0 plus b theta naught 1 minus. Okay, so now theta naught, when we take the inner product of this particular state with 0, we get 1 by root 2. And when we take the inner product of this state with 1, we get e power minus I theta L by root 2. This is because it's a minus sign, because here we are considering the bra of theta L 0, not the ket operation. So when we basically take its conjugate, Hermitian conjugate, then we get a negative sign here. So we're getting a negative sign here. Okay, so now using this particular formula, what we have obtained here, let's compute it further. So we get theta L naught tensored with 1 by root 2 a plus b into e power minus I theta L minus. And further we can expand out the plus and minus as 0 plus 1 by root 2 and 0 minus 1 by root 2. Okay, there's a b missing over here. Yeah, and so further we can just club these two terms, and we get a plus b into e power I minus I theta L 0 plus a plus b into e power minus I theta L 1. And this is nothing but the output of u of theta L applied on psi. So because we didn't normalize it initially, we will be normalizing it here. We can just remove this 1 by root 2, and we get the state to be theta L 0 tensored with u of theta L applied on psi. So that's why that's how by applying by first applying the CZ gate on psi and plus, and then performing the measurement in this particular basis, we can obtain we can kind of apply the single qubit gate u of theta L. So here we can see that the we initially had psi on the first qubit, but now that psi has kind of teleported to the second qubit along with a particular gate applied to that. So this is basically applying single qubit gates through MBQC, but this is just one particular gate, right? So how does this represent, like how is it possible that every single qubit gate can be applied in the same manner? So basically there's a theorem which says that it is known that any one qubit operation can be decomposed as u of 0 into u of theta 1, u of theta 2, u of theta 3 for some angles theta 1, theta 2, and theta 3. Hence, using this technique, we can implement any one qubit gate. And yeah, whatever I showed was for measurement outcome m equals to -1. Similarly, for m equals to 1. For m equals to -1, we get the state to be in this fashion where an x is applied. And we know what the measurement outcome is. So based on the measurement outcome, we can apply an x again and just cancel this x out. Yeah, so any doubts on this problem? Okay. So this last part of the problem, I'm not solving it. You can try yourself. We'll be giving you out the solutions, but it can be solved very similarly to the C part of the question, where first you have to compute. You have the states. That is, I'll just give you a brief idea. So here what we are doing is we are considering 4 qubits with the first and third qubits in states psi1 and psi2 respectively, and the second and fourth qubit in the states plus. And then we have to apply this operation, that is CZ21, CZ23 and CZ24 to the 4 qubits, and we obtain the state mu. So in the previous problem we had zeta, here we have mu. And then by measuring the first and second qubits of mu in the x basis, we obtain the state of the third and fourth qubits to be any of the following states based on the measurement outcome of the first and second qubits. So we are measuring in the x basis, so the measurement outcome is either plus or minus. So we get plus plus, plus minus, minus plus, and minus minus. And we get the C naught operation in each case, but it's applied by either an X or Z operation on the any of the two qubits over here. So yeah, hence we can even implement the C naught gate through MBQC. And you could, for these CZ operations acting upon these plus states, you could use the, I think, B part of the question. And yeah, as we are able to implement the single qubit gates and the C naught gates through MBQC, hence we can implement any gate, any quantum gate using MBQC, and hence MBQC is a universal quantum computation technique. Yeah, thank you. Thank you all. If you have any questions, I would be happy to answer.
Thank you, Dr. Priya, for that solution. Since there's no other questions about the problem set, we can proceed with the coding part of this workshop, this tutorial. So I'd like to welcome the members of the IndiQ community who are here to help with the coding part of the session. So the screen is yours. You can start. You're not audible. You're not audible still. You're not audible.
So, am I audible now?
Yes.
Thank you. So, hello everyone. Sorry for taking up your time. So, yeah, my name is Rahul Pratap Singh, and I'm here from IndiQ. So, we will give you tutorials about different topics which will be introduced by the speakers. And so, before going into that, let me tell you something about IndiQ. Who are we? So, IndiQ is a non-profit organization, and our aim is to make India quantum ready. We are basically a group of students who are trying to teach other students and learners quantum computing and making them able to teach others also. And yeah, so we do events, game jam, hackathons, all kinds of different fun activities, and which can also teach quantum computing. And our end goal is basically making quantum education accessible to all. So yeah, so that's it from IndiQ, and now I will forward it to Mitesh, who will tell you, basically give you a tutorial about QKD and answer your questions too. Hello, Mitesh, take it.
Yeah, hello, Rahul. Yeah, hello everyone. I'm Mitesh Adke, and I am a third year student at Pune Institute of Computer Technology, and I recently became a Qiskit advocate. So I will be implementing QKD BB84 protocol for this tutorial. So let me share the screen. Yeah, I hope my screen is visible. Yeah, is it?
Yeah, it's visible.
Yep. Okay, so So in the theory lectures, you might have studied what quantum key distribution is and even the B84 protocol. So I will just give an overview, and you might have to fill a single line codes in this tutorial as well. And you can get the link for the tutorial of GitHub link from us later. And so starting with key distribution. So what is key distribution though? So if you want to build a secure connection or communication between two parties known as Alice and Bob, so we need to have a shared key between them so that we can depend on that key and use that key to send messages with each other. And so the way of encrypting and decrypting these messages using that key will be showed in this tutorial, but in a quantum way. So what really is a quantum key distribution? So quantum key distribution involves the properties of quantum mechanics, which help to distribute the key among these two parties. So we'll be using Qiskit to implement the BB84 protocol. As you all know, BB84 protocol stands for Bennett and Brustad, those physicists who proposed the protocol. And the best example or where to start about this protocol is the Qiskit textbook. It's the reference I've given in the notebook. So you can go through this and read about a lot more of things from this Qiskit textbook. Basically, in this tutorial, we'll be showing like how the encoding and selection of the bases are actually done in code for Qiskit. So this is the layout where the QKD you might have seen in the theory as well. So we'll first select the basis for Alice, in which he will use this basis to encode later on. And same with the Bob, but here Bob will receive those encoded message from Alice and use that for the measurement. And in the third step, we'll use this basis that were formed in the first step to encode those bases into it, and then sending these encoded qubits to Bob through a quantum channel. And in the fifth step, Bob will measure the quantum states in the basis that he selected in the step 2. And in this step 6, so Bob will need to verify if he has got the correct bits and the qubits, so that he'll need a pre-shared, like from the classical channel, Alice will be sending those his bits as well, his basis that he's chosen, and the polarized formed output after the encoding part. So they will now finally in this last step, they will verify it and discard all the bits that aren't equal, and they will keep only those bits which are equal as the shared key between them. And depending upon the key, they will use that key to communicate, and such the secure communication is formed. So initially we'll start with the imports and installation, and so we'll be using 0.20.0 version of Qiskit. And so this is part you don't need to worry about. You just run it with shift enter. And so in the protocol requirements, so we'll first need a key length, so that we need to filter out, as I said, we need to later on select equal basis, equal bits that are gotten from the Alice and Bob's outputs results. So the final shared key will be less than 100. So you can manipulate it with, you can increase, decrease, it's up to you. And so this is just a hypothetical channel that I have set so that it would be easy to understand that we are defining a quantum channel as an empty list for now, and later on we'll append to that list various circuits later on, so that this circuit shows that it can be transformed from Alice to Bob. And the classical channel, as I mentioned, we need to transfer the basis for selected by Alice. So these are the two requirements, and the key length as well. And now the first step. So we'll be implementing a QKD. So we'll need first, the Alice will need some bit strings which are randomly selected, and he'll need to select his own basis which are also selected randomly. And we are considering that 0 means 0, 1 basis, which is normal known as Z basis, and 1 means the X basis, that is plus minus basis. So in computational basis are generally we represent while programming. So I've done is that 0 can be encoded as z basis and 1 to be x basis. So I have generated the random bits for basis and the bit string, and we'll obtain it when we call the function select encoding, and just to verify if we have got the right result. uh, and now in the step 2 we'll measure. So Bob needs to will need to get his own basis, so in which he can perform measurement when he receives the encoded bits from the Alice. So you can use the same code and fill it here, and you can try and run it, and you can use your different methods to get the random bits from basis. Just keep in mind that the Bob's bases are in the string, and the final obtained result will also be a string, and you have to give it to a variable, and this is to check if we have got the right result. And then and this is the important part where encoding comes in. And now Alice, with his bit strings and his basis, he'll need to encode these qubits, and the encoded qubit should be sent to Bob. So initially as I told, that Alice's basis as selected as 1, which was generated, can be told as 0 1 basis, that is z basis normally, and 1 denoted as x basis, that is plus minus basis. And now how does now we'll look into how a 0 passing through a z basis gives 0, and a 0 passing through x basis will give plus state. So usually the plus minus state, we can represent this with polarites. And so I have just given a representation. If the polarites are aligned vertically and horizontally, so this represents z basis, that is 0 1 basis. Uh, and if the state is 0, that is vertically aligned photon beams that passes through the polarites, will obviously give the same result, as it just passes through without any interaction with the polarite, and will get the same result. And the same with a horizontal beam of photons that we denote in computation as 1, and this 1 will pass through the z basis to give the same result. So we see that z basis does not actually perform any operation on them, but in quantum mechanics there is also a phase shift which is not shown here. And so if we align the polarite 45-degree with the tilt, then we get the x basis, and that is plus minus basis. And if we use now a vertical beam, that is the 0 state, to pass through this polarite, and it will give a plus state, that is in superposition. So BB84 is again using the superposition principle of quantum mechanics. So and we can see, I'll talk about why BB84 is not the best protocol. There are many other protocols in QKD as well, and I'll talk about it later. And in this so when these are horizontally aligned, photons are horizontally aligned, and it passes through the x basis, it will give minus 1 state, a minus state. So plus state, you might be knowing, is 0 state plus 1 state divided by root 2, and minus is 0 state minus 1 state divided by root 2. So this is how we obtain, and this table shows you, and this table will really help you to understand how the transition takes place and what is the qubit obtained. So using this table, uh, I've written the code. So in this code, as you can see, if you have 0 basis and 0 bit string, then you get 0 state. So initially all quantum circuits with its quantum state is 0. So I don't need to do any operation. So I didn't change it. So now that we know it is 0 basis, and now the bit string is 1. So we get output as 1. So initially all the states are in 0 state. So we need to convert it to 1 state. So I've used a X gate to convert it into a 1 state. So similarly, you can use this property to bring this into a superposition state. So how can we bring the superposition state? So it can be obtained by various ways, but to get an equal superposition, we use Hadamard gate. And to get a plus state from a 0 state, we'll need to only apply Hadamard gate, and you can do it just by implementing this. And similarly, when we have one bit string and one base, So we know that encoding basis is X basis, and now we'll obtain the result as negative state. So this minus state is, we need to first convert the qubit into a one state and then apply Hadamard gate so that we get the output as minus state. So this is how we encode qubits to, and we'll assign it to qubits encoded using this function encoding. And now we have once obtained the encoded qubits, we'll now send it through a quantum channel to Bob. So here is the quantum channel. I've just assigned it so that it just shows that it has transferred. So in the step 5, we'll measure. Now Bob has received those encoded bits from Alice from a quantum channel. Now he'll use uh, this bits to measure with his own basis that he obtained from the step 2. So you can see this function has an argument with his own basis. So and with the quantum channel, that is what he has obtained as encoded qubits. And now there is another argument that is backend. So I'll talk about it in the next cell. So initially we'll set as Bob bit string. So we'll now generate output with the basis and the encoded qubits that we obtained. Uh, so as we can see, if we get a 0 basis, that is the Z basis, and 1 as the X basis, as I said earlier. And so you'll need to just apply the Hadamard gate to get here. So not a single line code would be enough, and we'll get the measurement. So backend I've used this Qasem simulator, and you can use different simulators, or you can use the actual hardware. You'll just need to write a few more lines and you'll get the output. So once we measured these states, and Bob has now received his own bit string, now he'll need to verify if he has got it correct, and they will need to filter and select their own key now. So how do we verify? So we'll need another classical channel. It can be through wire or anything they can use anyhow. And so Alice will give his basis through that classical channel to Bob, and I've set it to classical channel Alice's basis that we formed in the first step. So now we'll need to find a symmetric key. So a shared key is what we want. So finally, once we get the shared key, the protocol is successful and we have developed a secure connection. So but how do we do it? So now that Bob has received everything and we'll need to get a shared key between them, we'll need to first find the positions where these qubits are same. So if Alice has sent his basis as 1011, and Bob has his own basis to be 1101, so he will check. So one matches to one, so the first position matches. So first position can be used as a shared key, and now the second doesn't match because it's 0, and third is 10, so discard. So last one is 11, so now we have got another one. So the shared key can be used as the first, and the fourth position can be used as the shared key. And now I've just used another function so that we can use while eavesdropping. So this is a key formation function. So it takes in the position. So now I have got first and the fourth position, as I said, and the bit strings can be any bit string. It depends upon who is it, if it's Alice, or if it's Bob, or Eve. So with this Alice bit strings will be used to form the key, Alice's key, through the classical channel, and that is Alice's basis. And Bob key will be formed through Bob bit strings and agreed basis position. So these are the positions. So with this, we'll get the output, and if this output is true, then we can say we have obtained a secure communication. And now that we have obtained a secure communication, and we can send messages through it, and this key can be used to encrypt the message and decrypt the message by the receiver. So just an example to show. So you can see this is how we get the output, and one matches to one. And so you can see Alice's key is matching to Bob's key, and and we obtain the result as true. So, and you can also see Alice's key is 51. So you might obtain different results for these two uh, when you run, because we have initially stated for random generation of bit strings. So the only thing you need to find is that you have formed a secure communication between them, that is, you get this as true. So this proves that they have gotten us a secure communication. So now moving further, this is just an example to show how we'll use an actual data to be transferred through encryption and decryption. So Alice's message will be encrypted by Alice, and that will be sent. So you can output it and see that so you can output and see how the encrypted message is different from the original message. And you can even use UTF-8 encoding for actual messages like text messages, images, and videos. So there is another part of code that you can also try and implement. And so just to verify that the original message is also should be same to the decrypted message by Bob. So if that's not the same, then there is no point in implementing. So here we get as same. So this shows that we have successfully implemented BB84 protocol, but we have only shown that this is the case where Eve has not interrupted in the quantum channel, and it has been very simple for both of these parties to communicate. But what if eavesdropping takes place? So if Eve tries to interrupt in the quantum channel, so the quantum channel behaves in such ways, as you know, if we are sending the encoded bits. So what happens is, if Eve tries to interrupt, and if he tries to see the messages, so here the interruption is uh, kind of a measurement that is done by Eve. So Eve will need to form his own basis, so that he will measure in his own basis, and he will see those bit strings, but the bit strings will move on further in the quantum channel to Bob. So the measured bit strings by Eve in his own basis will be moved further to Bob, and now Bob will receive a measured state, and Bob will perform his own operations. And after performing the operations, in the last step, he will realize that when he operates the key formation step, he'll realize that the output isn't true, it is false, and you can see it here. So the output is completely different, and it shows false when an eavesdropping takes place. So this is an homework problem, although I'm showing it to you. So Eve sets his own basis, and he tries to interrupt in the quantum channel, and he makes his own measurement in it, and then the quantum channel again encodes it and sends it to Bob. So Bob is now measuring the measured bits by the uh, Eve's measurement. So we'll get is a completely different output for Bob after his selection of basis and measurement being done, and you can see the output is false. So we can say that the channel isn't secure, and you will need to use some other channel or another states to again form a secure channel. So if we try to talk about disadvantages, it may be the case that we are also using these states only by superposition. What if we use entanglement? So it is beyond BB84, but there are few protocols that use entangled states, like E91 protocol. You can look for it afterwards. And there are few protocols like 6-state protocols, which include multiple states and multiple measurements and various other things. So BB84 has uh, has proved to be useful, but how many times will you keep sending those messages through quantum channel and through classical channel? So how do you know if the classical channel is not compromised? So this is also another disadvantage, and there are many other protocols as well you can look for. And BB84 was the first one and proposed, and this is how we implement it, and you can try out for eves as we have already implemented the functions. You just need to call those for making eves basis and making measurement for eve. And so finally, for if I were you and starting with the QKD, I would recommend you to start with the Qiskit textbook. And here is another implementation if you're really interested in implementing it at a large scale or industrial level. So this paper is really a nice paper, and you can look at it. So this is scale implementation of QKD. So that's it. Yeah. So if you have any doubts, you can ask, or maybe you can keep it at last. What do you say, Rahul?
I think let's let them ask if they have any
Yeah.
doubts. Yeah. You can either ask or send a text, and we'll try to answer them. So looks like there are no doubts. Praveen, should we go with the next one, or is there any other channel that we're missing where they might give doubts?
No, I think you can proceed.
Okay, perfect. Thanks, Mitesh. I'll take over from here, and I hope you can. Yeah. Okay. Hi, everyone. So today you've just learned about the communication side of things. That's QKD. Now what we're going to try to implement is on the computation side of things, a specific algorithm called Grover's algorithm, which I believe you guys have learned in the morning, and we'll try to implement it. But before we do that, we'll take about 10 to 15 minutes just to recap, and at the same time, learn a few things that will be helpful during the implementation. And so how this talk is going to go is it's going to be about 45 minutes. In the first 10 to 15 minutes will be a recap. And then we'll go into the coding part where there's two sections. The first section is we'll try to build Grover's algorithm for 4 qubits. But then after that, we're going to use Grover's algorithm to solve a specific real-world problem called 3-SAT problem, which is a Boolean satisfiability problem. And we'll also learn about what the problem is. So don't worry if you don't know about it. So I'm now going to share my screen and start with a brief explanation. Yeah. I hope you can see it. Perfect. And also one small reminder, if you have any doubts at any point in time, please do stop me and ask. That's why we're here. We're trying to make you, trying to answer any doubts you have and at the same time learn ourselves. So I'm going to start with Grover's algorithm. And I believe you guys have learned it, so I'm going to go a bit fast. At the same time, if you think it's too fast, do stop me. So as you know, like Grover's algorithm is a search algorithm, and let's say that the search space is n. Usually it'll take us n by 2 queries, but here it only takes us root n. And mathematically, how Grover's actually looks like is there's some bit string, and there's only one specific bit string, that is x0, for which a specific function becomes 1. That's what a search problem is. But using Grover's, we can actually, the function doesn't have to be like this. That means you don't have to search for just one value. You can search for multiple values at once as well. And we'll learn all about it. And before we go there, we're going to learn a few important things. And the first thing is an oracle. I believe you guys already know it, but just to give you an idea, it's a black box that does some specific unity operation. And you might have learned this part, but if we ask a question saying, create an oracle that outputs the state 1 on the 3rd qubit when the input on the first 2 qubits is 1, 0. So let's look at that. And so let's say that this is, the first qubit. They're both initialized at 0. And the first and second qubit, third is initialized at 0 as well. Now we're asking, how can we create an oracle that outputs state 1 over here? So it has to output a state 1 over here when the input is 1, 0. So for the input to be 1, 0, let's just say, we give an X gate over here. So now it's 1, 0. Now, how do I make sure that third qubit is specifically 1 only when we get this state? And for that, I could just say, I'm going to take something called you might have seen this gate, and I'd like to call it as an AND gate, because what it does is whenever the first two qubits are 1, the third qubit is flipped. And we'll use that gate over here. But before we do that, we will make sure that whenever the state is 1, 0, we'll convert it into 1, 1. And whenever the state is not 1, 0, it will never be 1, 1. And that's how we actually solve this problem. So to do that, let's say this is the part where we do it. And now over here, we get the state 1 and 1. And when we put Toffoli gate, we basically flip this third qubit over here, and then this will give us an output of 1 only when the input is 1, 0. So just keep this in mind. This is what we mean when we say an oracle, especially in this case, and it'll be helpful while we are trying to implement a 3-SAT problem. And one more idea, I'm pretty sure you know about this. It's phase flipping. So if suppose we have a state minus, and then we apply an X gate on it, then it turns out it becomes a minus of a minus state. And then here, this will be used, as you know, in growers to tag a specific solution so that later you can flip it, right? And here's just a small example that you can try. That is, this is the input state. How do you make sure that you bring it to this specific state and only flip 1, 0? So you've learned how to figure out whether or not the input is 1, 0, right? Do the same thing over here. Let's say you give in all specific states, that is 2 Hadamard's, and over here you create a minus state at this point. Now, what do you have to do over here such that you give a phase minus whenever you get a state 1, 0? And you know that if you flip a minus state, so if you apply an X gate over here, you will get a minus of minus. So what you should do is you should flip this. That is, you should apply a gate X only when you get an input of 1, 0. And we know how to do that. Whenever we get an input of 1, 0, you apply an X gate. Then you do this, right? And this third qubit is flipped only when the input state is 1, 0, right? Are there any doubts at this point? If not, I'll carry forward. Yeah. So this is how you can use the previous idea of creating a specific oracle and the idea of phase flip to tag a specific state, right? Okay. And very quick recap over here. That is, how does Grover's algorithm work? You initialize, then you apply an equal superposition. That is, you apply all Hadamards. What you're doing here is you're giving it a chance to look through all possible states, and then you flip the phase, similar to what we did before. You flip the phase of the specific state that you're looking for, or the search state, basically. And after you do that, you apply something called a diffusion operator, which will just, in general terms, it will increase the probability of the tagged states. I like to call them tagged states. It's nothing but the states with that negative phase over there. So if you do the diffusion operator, it's going to increase the probability of them showing up, and then you can directly measure, and you will get that specific state most of the time. Yeah. So just to understand the diffusion operator, you guys probably already know it. I'm just going to go quickly through it. Over here, if suppose this is the input, and then you flip one of them, that is, you put that minus phase, and then the mean comes down a bit, and then you do a flip about this mean. When you do a flip about this mean, this goes all the way up there, whereas all of these only go till here, and that is what you're seeing over here. And this operation can be seen as minus v plus 2a. I know you guys already know that. In the morning, it was probably given as I minus, it's given as minus I plus 2a, right? And now let's just look at how we can implement this specific operation in a gate-based system, right? And to do that, identity, we'll look at it in terms of matrices, and the average matrix can actually be written this way, where let's say there's A, B, C, D, and then each of these are multiplied with A, B by N, C by N, D by N. The output that you get is A plus B plus C plus D by N, and that is the average, right? So over here, you are supposed to create this specific state, and this specific state actually looks like this, where it would be better if you can just go and try to do it on your own. Take a Hadamard state, and then Hadamard gate, and what I mean by 0n is 1, and then like the size of this is 2 to the power n, right? And try to do this and you will get this answer. So you'll know that what you're looking for, that is the operator that gives a mean, is actually this operator. And we already know how to implement this, right? We already know how to implement this as well. So all you have to now implement is this specific part. So the Hadamard part just comes out, and because Hadamard cross n and another Hadamard cross n gives you identity, so you're basically taking this identity, splitting it into 2 Hadamards on n qubits, and then taking it out directly. So this is what it looks like. You can ignore this because you already know how to put n Hadamards. What we are trying to find is, how do you represent this on a gate-based system? Let's just look at that quickly. Again, any doubts at this point? Please keep putting the doubts. It's a good sign that you're following along. Okay, so to do that, let's just look at what this operator does on the basis state, right? So if you want to look at what an operator does, you just have to look at what it does on the basis states, because any state can be represented as linear combination of the basis states. For example, if you want to know what a single qubit gate does, you just have to see what it does on these 2 states, because any single qubit gate can be written as this, right? So all you have to see is what it does on these basis states. So let's look at what it does on the 0 state for n qubits. And it just gives us 0, right? Because this 0 over here, and then this is 2 minus 1, and you get this state. Whereas for any other state, these 2 are orthogonal. So you basically, you get a 0 value over here, but this phi gets multiplied with minus I, and you get a minus phi. So, the point over here is, whenever you're giving a state 0, there is no phase happening. But whenever you're giving a state of anything else other than 0, a phase is being applied, right? So let's just see how you can implement it. And the best way to think of this is actually look at what is happening. So this is the circuit that does it. What does it mean? Like, how did you come all the way here? If you see, whenever we give a state of 0, all of these x's make it a 1 state. 1, 1, 1, 1. And then this gets triggered. And because there's a 1 and a Hadamard, this is nothing but a minus state. When this gets triggered, you're doing a flip on a minus. And we know that this gives us minus of minus. And there you go. You have the phase. Whereas for all the other states, so for 0, 1, whatever, this doesn't get triggered, and you do not get any phase. So over here, you're actually getting the exact opposite of what you require, but it doesn't matter because you can ignore it as global phase. But so now you know how to implement this. We have kind of learned how to implement an oracle. You know this, and right now you even know this. So you know the whole problem. You know how to implement every single part of the problem on a quantum computer. This is where we're going to switch onto the code and then look at how it's done exactly. And I'd like to stop for a minute and see if there's any doubts at this point. Because understanding this means that you've got 60% of what you need to learn today. Yeah. Okay. I believe there's no doubts. Right. You can also just raise your hand and I'll ask you to doubt. Okay, fine. I'm going to share my screen. Just give me a second. I hope you can see the screen, right? And just so you know, the code is all given in the GitHub repo that we have linked to. It's right here. If you want to know how to get this, it's a bit confusing, but you can just click on draw and then Control S for save, and then you can save it as a non-text file, so not a text file, and that should give you the code in case you don't have it yet. Right. Okay. Okay, fine. So now we have learned how to actually do it on paper. Now let's see how it's done on a specific programming framework called Qiskit, which is by IBM, and you know all about it. But again, if you don't have Qiskit, you can just run this cell and it'll install Qiskit for you. We're looking for 0.20.0. It'll mostly work for any other version as well, but just to be safe, right? So now to build our circuit, as you've seen the part like the meat of the equation, but there are a few other important things to note. That is, to implement a few gates, for example, if you want to implement a multiple controlled NOT gate, that is, you have 3 dots, 3 control qubits, and then you're trying to do an operation on the 4th qubit. And you can just write it in Qiskit called an MCT gate, but that will actually lead an extra qubit, an extra clean qubit, that is a qubit in the state 0, for it to do its operation. And these extra qubits that are not part of your logic, but they're required for you to do your logic, are called ancilla qubits. And we'll be using them, and we'll need 2 of them. And the algorithm that you're doing is for 4 qubits, and we'll try to find the entry 1010. It's a bit contrived because you already know what you're trying to find. I know it's a bit confusing. I was really confused in the start as well. But later when we're working with 3SAT, we'll get a brief idea of how we can use Grovers to find something, right? And OK, so let's now build our circuit. We need 4 qubits. You need 1 qubit to store the state minus, because that's where you're going to do the NOT, or that's where you're going to flip it so that you can get a specific negative sign over there for the qubits, for the states that you're looking for. Right? OK, so first, there's a bit of initialization happening, Matplotlib, NumPy, and Air, and quantum circuits, etc. And also you need to import this for visualizations later. But how we're going to do this is, first we're going to create something on a quantum register, which is, as it says, the number of qubits that you're looking for, and then a classical register for the number of classical bit spaces that you are looking for, where you want to store your value after measurement. So after measurement, as you know, it becomes a classical bit, and you store it here. And you can create a quantum circuit this way. And the first step that we do in Grovers, as we saw, is after initialization, we put it in an equal superposition of all states. And that's what we're doing over here by putting the first 4 qubits in an equal superposition. And the 5th qubit, we're using an X gate before it so that we can make it into a minus state. That's where we're storing a minus state. And you may ask what's 5 and 6, and that's what are the ancilla qubits, and we look at them below, right? Okay, just to recap, this is the complete diagram for the equation. We're done with this part. Now we have to implement an oracle. Yeah, and to implement an oracle, we are searching for the state 1010, right? Let me just start running the code. So we have to implement, we are trying to look for the state 1010. How do you do that? If you can look at the circuit over here, it seems pretty obvious now, because if the input is 1010, after these 2 X gates are applied to it, it becomes all ones. And we know that whenever we have all ones on all the controls, then the operation happens. That is, the flip happens. And we're doing the flip on the minus state so that you can get that specific tagging, that is the phase on that specific state. And later, it's almost autopilot. That is, the amplification step is going to just amplify the probability of you finding that tagged state, and it'll do it on its own. But the part where you have to actually go based on what type of question you have is while you're building the oracle. So while building the oracle, you have to keep in mind what you're trying to do based on your problem, and build it in such a way that your answers will be tagged with that phase. Okay. And this is obviously not the best way to do it, but this is the simplest way to understand. You don't have to, you can just do a Control Z operation if you want. Are there any doubts at this point? Just want to see if there's any doubts. I guess that's a no. Yeah. Okay, so let's recap. We're done with the first step. We're done with oracles. Now we're doing the diffusion operator. And this is the part that we just learned. That is, to do the diffusion operator first, there's just Hadamard's on both sides, fine. And then you do that I-2 times the average part. And how that looks like, as we've seen, is all X, H, and then a controlled X, and then the same thing again. Yeah. Also, yeah, okay, this is fine. And there's one important thing to see over here. That is, it's overlooked most of the time, but it's good to keep note. After we apply these x and x, and we apply this multiple CT, what's the reason for us to apply these two x gates again? And if you look at it, they seem redundant, but they are required because these are your inputs. I mean, the things that are coming over here are your inputs, and those you might use them later. So you have to negate the operations that you have done on them, and what we could call that is cleaning the qubits. So you clean the qubits so that you can reuse them. In most of the cases, you put a few qubits in state 0, you use them whenever you need them, and you clean them and then reuse them. But over here, we have specific inputs which we are modifying, so we have to remodify them to make them the original inputs, right? Okay. And in the end, we just add measurements. Seems pretty simple. Okay. And after we do all of that, this is the step where we are simulating it. Again, we're not using a real quantum computer to do that. There are other methods. It takes a while to do it on live. So for that reason, I haven't done it. But you can always check for that code, and it's pretty simple. You just have to change what backends you're using. And over here, we're doing something, again, important called shots. So, we don't emphasize this much while we're reading, but there's an important thing over here. In Grover's, as you know, we're increasing the probability of a specific state showing up, but doesn't mean that the first time that you do it, you're going to get that state. And you don't even know whether or not you've got that state. So for that reason, you have to reiterate this operation a lot of times. I mean, you have to do this whole algorithm a few times and do those measurements a few times so that you get like, okay, I got the state 0000 49 times. I got another state a lot more times. And then when you visualize it, it looks something like this, where you see that the state 1010, it's usually flipped in Qiskit. The state 1010 has the most number of occurrences out of the 1,000 that you had. So that's how you use Grover's to actually search for a specific sequence or search for a bit. And just a few important points. Just doing it one time has given us a pretty good answer this time, but that's not always the case. And in fact, we can increase the probability of this to a certain extent. And the number of times that you want to do these is usually root of n. And if you want to understand why it's root of n, I would suggest just doing it on pen and paper for like a small example. And then you'll see that it'll go something like this. So if the number of searches keep increasing, your probability will increase, and then it'll go down and then increase, and it'll be a periodic function that way. So you have to know at which point you have to stop so that you get the highest probability of your specific state showing up. And this changes based on the number of answers that you have. So if suppose instead of looking for one answer, you're looking for 3 answers. So I'm looking for 0, 1, 0, 1, 1, 1, and 0, 0, 0. Then I will have to do a root of capital N by M. And capital N in our case over here would be 16 because there are 4 qubits. And based on M is the number of things that you're searching for. Okay, and that will actually, change the complexity of the algorithm. Not much. It'll still be the order of complexity will still be the same. I mean, the speed might increase slightly. Yeah. So that's Grover's algorithm in its entirety for a 4-qubit system. I just want to see if this made complete sense to you. And are you guys even able to run this, or are you having some installation issues or any issues like that? If you put it there, Mitesh or Rahul will attend to them and help you set up your computer. I just want to see if there's any doubts either on the concept side of Grover's or the implementation part. Nope. Okay, fine. So moving on, now we're going to use what we have learned, that is Grover's algorithm, and try to solve a specific problem called a 3-SAT problem. So what is a 3-SAT problem? It's nothing but a Boolean satisfiability problem. So it's in the name itself. That is, all the variables are Boolean. They're either true or false, 0 or 1, whatever. And you have to make sure that you find a sequence that satisfies the problem. For example, this is a specific function, and v1, v2, v3 are our variables. And just to give you a bit of nomenclature, each of these are called literals, that is v1, v3, and basically this whole thing is called a clause. Okay, and you have an or and an and over here, and they have other names as well. Or is called disjunction and is conjunction, and this specific thing is called a negation. That's not, basically. Okay, if the X gate had been applied to, shouldn't we get the higher probability against? That's a good question. So Sukanya is asking a question over here, which is, we applied the X gate to states 0 and 2, but why are we getting a higher probability for 0, 1, 0, 1? So that is just a characteristic of Qiskit, where they're flipped, actually. So in fact, what we actually found out there was 1, 0, 1, 0. And you can actually test that out. Like, you can go, let's see. So instead of applying this oracle, right, and we've applied it to states, and if suppose we are to apply it to states 0 and 2, let's say. Same thing over here, 0 and 2. Let's see, oops. Start this again. Okay, fine. And if I keep going that way, now you can see the state 1, 0, 1, 0. So it's actually just flipped, and that's just something which is going to take you some time to get used to. Yeah, and they have an explanation for it. I don't buy it, but they have an explanation for it. Yeah. Maybe Rahul or Mitesh, if you can find that explanation, you can just put it here in the chat.
Yeah, it's that Qiskit uses Littleidian notation, and normal quantum mechanics is just the opposite representation.
Okay. Yeah, I hope that answers your doubts, Sukanya. Awesome. Okay. Is there any other doubt? Okay. Moving forward, now we're going to try and solve this specific problem. It's a 3-sat problem. And I hope you understood what the problem is. We're trying to find the values of V1, V2, and V3, which can only be true or false because they're Boolean variables, in such a way that your complete function that is denoted by this turns out to be true, right? And I've just drawn, I mean, you could actually do this using brute force. You could take all the possible inputs and then see whether or not they satisfy. This, as you probably can understand, becomes hard when you increase the number of variables because it becomes exponentially hard. And over here, you can see that there are specific places where they're not satisfying. That is 0, 0, 1, 0, 1, 1, 1, 0, 0. I urge you to just put these values in and check for yourself. I might have made a mistake, never know. But this is what the truth table looks like. And now we've done it classically using brute force. How do we do it on a quantum computer? Using Grover's algorithm. And as you can see, we're basically searching for all the specific answers. That is, we're searching for these. The ones that are marked with, the ones that are marked with 1, we're searching for them. And the analogy isn't exact, but it's still a search problem. And we'll see how we can convert it into a search problem. So how do we solve this problem using Grover's? To solve it, maybe let's take one step back and then separate it. We'll say, okay, now we have these clauses, and we know what the clause means. It means there's a not on a V1. So whatever the variable of V1 was, we flip it. And then there's an OR, so we have to do some sort of quantum OR gate, and then an OR, and then finally, on top of all of that, there are AND operations. So if I just split this into the clauses that are there, that's one clause, this is the second and the third, I can say that if I can find the value of what is happening in these clauses and store them in 3 different qubits, later, all I have to do is do an OR AND operation on them, right? Because if I know the value of this, this, and this, then I just do an AND operation on them, right? And then we can get the value of f, the function. So keeping that in mind, let's just forget about the AND operations, and we'll concentrate on each of these, each of these clauses. And as you can see, the main part in this clause, you know how to do a NOT, right? It's just an X gate. You do an X gate and you get a NOT. But how do you do an OR gate? That's what we're going to look at. And one thing to keep in mind is we need a 3-qubit OR gate. So 1, 2, 3 qubits. We could do away with 2-qubit OR. and I'll tell you how, but 3-qubit is a bit better. Yeah. So starting with the 2-qubit OR gate, and this, as you can see, is the truth table for an OR gate. So if you can look at this, let's start with 0 and 0. So whenever 0 and 0 are the inputs, answer is 0. You don't have to do much. You put 3 qubits and you initialize them in 0 state, and that satisfies. But if suppose you want to put, and if suppose your state B is 1, then you need your output to be 1. So then what you're going to do is you're going to apply this control NOT, right? Because from the second qubit to the third qubit, because you're saying whenever the second qubit is 1, I need the third qubit to be 1. So I'm going to do a control NOT, that is a C0 gate. And similarly, to satisfy the third thing that you have over here, you're going to put a C0 from the first qubit to the third qubit, right? Whenever my first qubit is 1, I have my third qubit to be 1. But if you put 1 and 1, this gets activated. So there's a flip. The third qubit becomes 1. And then if suppose the second qubit is also 1, it gets flipped again and it goes down to 0. So in this specific case, we're getting 1, 1, and 0. But you need 1 over there. So what gate can you put over there which does not affect any of the other inputs, but gives a 1? And you have a clear option, that is an AND gate, which only affects whenever both of the answers, both of the inputs are 1. So for that reason, we put an AND gate over here. There's no exact science to it, at least from what I know. But the best way to do it is actually sit down and try a few operations and think of it in a classical sense, and then try to convert your ideology into the quantum sense. But yeah, if there's any scientific method to find algorithms like this, do let me know. I'd love to know, actually. Yeah. So this is a 2-qubit OR gate. And you could do the same thing for a 3-qubit OR gate. You could say, I will store the value. I'll take an extra qubit. I'll take something like an ancilla qubit, and I'll store the value of the OR of the first 2 bits in that ancilla qubit. And then I'll take this ancilla qubit and an extra qubit. That's my third qubit. And I'll do an OR again. So basically, there are 3 things to do an OR between. I do an OR between both of them, store it in another qubit, then do an OR between both of these. And that will be my OR. That's fine. You could do that. But there's a more slightly elegant way to do it, which actually turns out to require the same number of qubits. So you might as well have done the other approach. But here is another way to do it. And if you, again, go through the truth table above and put these specific inputs, you'll see that it satisfies. Yeah. And the ideology is very similar to how you brought out an OR gate for 2 qubits. Right? Are there any doubts at this point on building a 2-qubit or a 3-qubit OR gate, or why we're even doing this? If you have any doubts, please put them there. Or you can unmute and ask as well. Yeah. Okay. Okay. So one thing over here. Now we are all ready. We know how to do a NOT. We know how to do OR operations. Now you know how to bring out each of these clauses. So whenever I get a specific clause, I know how to compute the result of this clause. No issues. And you also know how to put an AND gate, which is nothing but control how many times you want, and then do an X gate on the last one. So now you know everything that you need to know to do this problem, and then let's just go forward and do it, basically. So for this, we have to do a bit of a segregation on the number of qubits that you have. I'm taking 8 qubits. And the reasoning is the first 3 qubits are our input. Those are the variables V1, V2, V3. And the third qubit is the qubit where I'm storing my state minus, which I will need to flip every time that I find my answer, right? And the next 3 qubits, 4, 5, and 6, are the intermediate qubits where I'm storing my outputs of each of these clauses. So right here in our question, we have 3 clauses. You have this, the second clause, and the third clause, and every time we are going to write an oracle, which is going to find whether or not it's true, and if it's true, it's going to flip this extra qubit where we are storing its value, right? And this is done for these 3. For each clause you need 1 qubit, and that is why I'm taking 3 extra qubits over there. But let's say there's more clauses, then you need more qubits over there. Right? Okay. So this is how you can, this is how you should segregate. And I'm also taking 1 extra ancilla qubit. And this has to do with usually the multiple controlled NOT gates that we have over there. So I think I haven't explained properly what that means, but during this amplitude amplification step, oops. Okay, yeah. So in Qiskit and multiple control NOT gate, you can call it using MCT, and you can actually go to the documentation. I'm not sure if this link will work now, but you know, if you go into the code and you actually see, it requires n-2 ancilla qubits, where n is the number of controlled qubits, and that is the reason why we are taking an extra qubits whenever we require. So if you want to understand, maybe a simple way to understand would be, maybe they're just doing the OR gate twice or something similar to that, right? They're storing the value and then they're using that value to do the operation again, right? Okay, so that's why we require this extra ancilla qubit over here. And if you look at what we're doing over here, we're doing the same thing that we did before to build our Grover's algorithm: initialization, then putting everything in equal superposition. Why? Because you need all specific states to search in. If you don't need to search in a few states, you don't put those states over here. As simple as that. Right? And then we're also creating the minus state qubit over here, right? And let's just run it and see if it's working. Perfect. And now we're going to create the oracle for this, right? Oops. Yeah. So if you want to create an oracle for this without actually looking at what the answer is, I would argue that because it's V1 has a negation, I mean, I need to know when this thing will be false, right? So when will it be false? This is an OR operation. So all of them have to be false independently. That means that V1 has to be 1 because you're putting a NOT over here. This has to be 0. This has to be 0. Right? And that is when it will be false. Fine. And in all the other options, it will be true. So what we're actually trying to do is trying to find the times when it will be true and then making those times true. So for example, I know that's a confusing statement, but what I'm doing over here is I'm just doing a negation on V1. So whenever the input is 1, 0, 0, I'm supposed to get false, right? And this circuit that I wrote over here is the 3-qubit OR circuit. So what does the 3-qubit OR circuit do? If we just look at what it does, it gives 0 only when everything is 0, which is what OR means. So what you have to do is whenever the input is 1, 0, 0, you have to make it 0, 0, 0. And no other input should become 0, 0, 0. And it's pretty simple to do that. You just put an X gate over here. When you put 1, 0, 0, it will become 0, 0, and 0. But when you put any other input, it will not be 0, 0, 0. And because it's an OR gate, it will always get triggered whenever the input has at least one non-zero value, right? And then I'm storing the value in qubit number 4. And that's what I'm doing. I'm doing the operation and storing it. Similarly, I'm going to do the same thing. And yeah, again, an important note is you've done this operation fine, but you have to reuse these qubits later. You need the values. You don't want to use the changed value. So you apply this X gate again so that you negate the value, negate the change, basically. And you get your actual inputs, right? And as you see, no other change is happening in the middle because all of these are just controlled control parts. They're not doing any operation on that qubit, right? Okay, fine. So this way we can do the first oracle. Similarly, you do the second oracle. I'll leave it to you to find out how. And the third oracle, and you just append all of them and make sure that you store the values in different qubits. So for the second oracle, I'm storing it in 5. Third oracle, I'm storing it in qubit number 6. And after all of this is done, now I have done all of my disjunction or all of my OR operations, and I have 3 outputs. Now, if you remember, I have to do AND operations in the middle. And to do an AND operation, I'm just using the multiple controlled NOT or multiple CT operation. And that is just this, which is saying that whenever these 3 are true, then I'll do a flip on qubit number 3. And what did I have on qubit number 3? I had the state minus. So when I do a flip on the state minus, I get a negation, or not negation, I get an extra phase applied. And that's how we can tag that specific solution of ours. And once we tag it, Next, as I said, it goes into autopilot mode. Amplitude amplification does its job and amplifies the amplitude of your answers. And that, as you can see over here, is nothing but the same circuit that we saw earlier on how to create an amplitude amplification step. And one important thing to keep in mind over here is I'm only doing this whole operation once. I would suggest you try doing it a few more times, maybe write a function and just iterate and see how your outputs change later on. And we'll actually look at a small, not an anomaly, but something that you wouldn't expect. Yeah. So next you add your measurements. I'm only measuring the first 3 qubits because those are the outputs I require. Then after I run the circuit, I'm actually getting something over here that is not what I expect. So let's just quickly go all the way up, not all the way up, but oops, yeah, over here. And let's look at the values that were not supposed to, that we didn't, the values that gave the value 0. Those are 0, 0, 1, 0, 1, 1, 1, 0, 0. Just quickly remember that. When we come and look at the values over here, you see that 0, 0, 1, 1, 0, 0, 0, 0, 1, and 1, 1, 1, 0, and 0, 1, 1. These 3 states were supposed to have a lower probability, but turns out they have a higher probability. I'd like you to just think for a few minutes and figure out why this is the case. It's actually something which is interesting. And if anyone has the answer, do put it over here. But just to give you a hint, it has something to do with the number of iterations that I've done, or any other step that affects the probabilities, right? And that's it for the talk or the tutorial. And all the code is here. You can just change whatever part of it you want and experiment on your own. I do suggest you do that. And just for the people who are more curious, there are a few other things over here. You can go to the Qiskit notebook on satisfiability, and over here you can actually use their inbuilt function to do everything that we have just done. And this is also a good reminder for you to see how much effort it goes into making an algorithm like that on for any which takes any input and does the job. I would suggest you try that out as well. That is, you repurpose this for any SAT problem. So 3 SAT is because we had 3 variables in each clause, or 3 literals in each clause, but it becomes KSAT when there's any other number. And yeah, that's it. Try to reduce the cost of the circuit, and that you can do. And what I mean by cost is given in the Qiskit Challenge 2019 notebook over here, right? And a few other steps, next steps, I would say 100% go and look at this. That is, I believe this one. So they have a beautiful challenge over here, which is a graph coloring problem. And you can solve it using Grover's algorithm. This is how I started into quantum computing, and I would urge you to go and do it out and test it. And there are also a lot of solutions for it given by the top scorers. Yeah. But yeah, that's it for everything. And if you want to learn hardware, then go and search on Qiskit Metal. If you want to learn about what happens below the qubits, that is, how are these qubits actually affecting how are these gates actually affecting qubits? That's done by sending pulses, and you can read about Qiskit pulse in this specific chapter. But yeah, that's it for the talk. If you have any doubts, do let me know right now. And then next we'll jump to Rahul, and I'll give you another beautiful talk. Yeah.
Yeah. So
I believe there's no doubts right now. So I'm going to stop sharing. Again, you can just put your doubts over here in the chat, and I'll tend to them. Yeah. Okay. Thank you so much, everyone. Yeah. After Rahul.
okay, let me see. So is it visible now? The screen?
Yes.
Hello. Okay. Okay. Yes. So Rana and Mitesh both are done with QKD and Grover. So I'm not going to explain too much. I will take a pretty simple approach to quantum error correction. And you have, as Rana said, there are hardware part to quantum error correction that you can read, which also reduces error. But I will keep myself to the basically the theoretical part or the software related part. Call it software. It's not actually software, but you can call it that. Yeah. So but before going to quantum error correction, bit about classical error correction. It's basically a simple example is that if you call someone and you are on a noisy line and the other person asks you, hey, you want ice cream or not? So, and the only possible answer is yes or no. You can't give any other answer. So what you do is that you repeat multiple times. You say yes, yes, yes. If you want to say yes or no, so no, no, no. Yeah, it is done because in case the person is not able to get the answer first time, he can get a second time. And in total, if it is not clear all the three times, what he will do is he will just take the majority of it. So if two times he interpreted yes, he will think, okay, let's go for yes, or twice no, then no. So yeah, and simply it's like by imagination you can know repeating multiple time increases chances of getting correct final outcome, but there is this derivation, simple and easy derivation, which you can look if you want to. It says the same thing, that increasing repetition helps into reducing error due to noisy channel. And quantum error correction by repetition code is similar. You do the same thing here. You make multiple copies, and then error occurs, and then you decode them. But you know, right? No cloning theorem doesn't allow you to copy. So how to do it? How to actually create copies and use this classical repetition code technique in quantum? So one thing is that you can go through this whole derivation and find it out, but I don't like it. I don't like the way to go into the derivation and then doing it. Or rather, we can just look through the code and I can tell you. So this is basic installation step. You can just run it if you want to. But yeah, coming up to this part. So any error correction technique can be divided into three steps. One is first to encode. So this is the part where you encode. Then this is not a step, but some error occurs, and then you try to decode it. So this is decode, and then you get the final outcome, that is after the measurement part. But in this one, we will take a different approach. What we will do, we will first encode, then run the circuit, take the measurement, and then interpret that where error might have occurred and what can we do to interpret the correct outcome from the errored outcome. Because this is the one technique which people have tested and is working right now. You know, current quantum computers have too much error to be so that it's not possible to use something like a whole you put up a whole bit flip circuit and run it. Most probably what it will do is that due to more number of C nodes, it will include more errors rather than reducing errors. So this is the way we use. We encode the data, we measure it, and then we see that what changes might have occurred. But this doesn't mean that after encoding we don't do anything. We also put up a detection part over there, which tells us, okay, this might have occurred. So going to the part where encoding. So in simple words, here, if you this circuit will help us visualize. So here at the starting, Q naught can be any psi, but and the any psi derivation is here. So you start with some random psi, and then you encode it. And how do you encode it? It's simple. It's for there are like two kinds of encoding which I will use here. So starting with bit repetition, is that what I do is basically, if I have 0, I make multiple copies of 0, and for 1, multiple copies of 1. And yep, so how to do this is just using C nodes. So no cloning theorem says that you can copy states which are orthogonal to each other. So that's what it is done here. These two C nodes are basically copying or creating this state A 000 and B 111. And after that, once you are done with encoding part, do not look at the detection part first. This is the encoding part. Once it is done, you need a simple error model. What I have created here, it's you can create it also. It just randomly chooses one of the three qubits and put a X gate over there. And why X gate? Because X gate represent bit flip, and bit repetition code is used to detect bit flip. Here, you can get this notion simply by that X changes 0 to 1, and that's a bit flip in simple sense. Going forward from there, what after that you need to do is to create something that can basically find out in which of the repetitions error has occurred, but uh, without destroying them, basically not a bit without measuring them. You want to keep the encoded state alive for a longer duration. You see there is no measurement here, but you want to check in which of the qubits error there is an error, or flip gate or an X gate is there. So what you do, simply let me just take a yes, please. Yeah. So in case, uh, assume that you had something like A000 plus B11, and okay, so let me just take simple A00 triple zeros. A longer derivation is given above. But in case, let's imagine an X gate occurred, and what's the resulting is the mid middle qubit flip. Then you will have something like this 0 1 0. So you need an operation which will tell you that middle qubit is flipped without measuring all the three qubits. So what this operation will do, it will measure two qubit at a time. So you first check for 0 1 and find out, okay, these both are not same, and you say 1, not same 1, and same 0. So you ask uh, uh, 2 and 3 and check if they are same. No, 1, and then you say okay, 1. It means that um, this one is not same to this one, and this one is not same to this one. And since there are only two possibilities, you will get that it's the middle cube, that is the second cube. And let's try another example. If the last qubit flip, then you will see then you will let me just have some space. If the last qubit flip, then you will get 0 0 1, and then you check again first two, then they are same, that is 0, and the next two, basically the last two, then you get 1, not same. And then you see, okay, 0 1, it means definitely last one has flipped. And don't worry if you are not getting why what I'm getting from these to the what is flipped. I have this table for you, which will help you in finding conclusion. So if you get 0 0 all same, 0 1 qubit 0 is flipped, I count from 0 1 2, and same as Qiskit. So 1 0 2 or 1 1 first qubit. And there is no big thing going on behind it. It's simply what it's doing is doing majority voting here. So this whole operation from comparing to this conclusion is majority voting. It's just asking all, it's similar to asking all three of them that what are you, what are you, what are you. If they say, if a majority of them say 0, then 0. If 1, then 1. Yeah. So how to create this comparing circuit? So what we do is again game of C notes. So two C notes again. What it does is that you use this one on this qubit. If this one is 1, it will 1 again, and if this one is 1, then it will be again. Else, if 0, no. So if both are ones, then it will flip and flip again 0, and if both are 0, flip flip, no flip, no flip, 0. The only possible case this output can be 1 is that these two are different. and that is only possible when one of them has error. So this is like one simple comparison for 0, 1, and similar you can do for 1, 2, and then measure it. And this measurement won't disturb your 3 qubits on which data is stored. So you can repeat this operation multiple times during the time of the qubit to check that if there is some errors occurring over there, and check if you want to after how many repetitions this error occurs. So before moving to the part that what you can do with it, let's also look at phase repetition. So derivations aside, it's all there, but it's similar to what you did here. The only difference is encoding technique changes and also the detection techniques. And yep, error, it is represented by Z gate. It gives you phase error. And yep, one simple way to check it is simply doing it here. So if you know flip is done by 1, then yeah, so 0 to 1, this is flip, that is X gate. And also if you want to see why Z gate represent flip errors or phase errors, you can basically create a plus state, put a Z gate, you will see it change from plus to minus. And if it was a minus state, let me create one. If it was a minus state, then another Z gate creates a plus state. That's why phase flips. So okay, Z gate represent phase flip. You can create a simple error model like that. Now creating the same thing again. So first thing comes up is that you have to create a code which creates a phase encode. So basically, if you had plus phase between A and B, it should create something like this. So it's not exactly plus, but you can get the gist of it that it creates phase encoding. All the derivation is here if you want to look at it, but in simple terms, it okay. Yeah, before going much into phase, if there is any question about bit, please ask. Okay, so yeah, continuing on phase again. Yeah, so once you encode phase information, then create something that would add a phase error, you do this um, comparison operation again. Most of some of you might know what these comparison operations are called. They are stabilizers, but I won't use that name because for now I'm assuming that people don't know about stabilizers. So yeah, again, yeah, the same comparison operation I do for 0 and 1 qubit, and then 1 and 2 qubit, finding without destroying the whole thing. Now coming to Shor's algorithm, but not taking Shor's algorithm as a whole, but rather than using the Shor's encoding only. So Shor's encoding is a mixture of phase and bit. So what it does is that first encodes phase and then the bit. And I can show you basically here. So what it did here is that first encoded phase into 3 qubit and then used each qubit to create bit encoding. So for one of the phase encoding created this 3, and then another one this 3, this 3. And I used a bit modified error model here, is that it uses PQ as a random number of all the available qubits, put up a X and Z gate over there, and for the time being, you are not informed that which one is this. So this whole thing won't give you any answer unless you draw the whole circuit. You won't be able to know till the step. You don't know. So you have to decode answer from this one, and you know if you get your output as something 0, 1, you can use the table to find out what is the answer. Yeah, so moving forward. Then for Shor's encoding, what you have to do is to create a whole comparison operators for this. So now what you do, you go step by step. So first, what you do, you create a detection for 0 1 1 1 2, 0 1 1 2, then 3 4 4 5, and moving on till here. So you get for all of those till 6 7, yeah, sorry, 7 8. You have all the bit ones corrected, and then you compare phase. For phases you use 3 because you know, right, 3 qubits are the ones representing each of the phase. So you compare first 3 with the second 3, and then second 3 with the last 3, and then you get some answer. And how do you decode it? Simply start reading from this side. So you know that first 2 qubits there are no change, they are same. Second 2 same. Last, but last 2 no. So it means that these two says that okay, there is no error in 0 1 2, happy. And this one says no error in 3 4 5, but this one says there is something in uh, 6 7 8. Yeah, so there is something in 6 7 8, some bit flip, and this part is only for bit flip till here, and after that there is phase. So you see, there is 0 1 means go to the table and see which one is the issue. Then you will say oh yeah, 1 0, sorry, 1 0, then qubit 2 is flipped, and you see qubit 2 is flipped according to this. And yep, qubit 2 means if you count from here 0 1 2, q8 is 2. And now using other part for phase. So yeah, so yep, let me see. Okay, yeah, so yeah, for phase same thing. It says yeah, so no change in the first two. So two blocks are completely same. 0 1 2 and 3 4 5 are same when you compare. Okay, good. And the next two is 0 1 1 0 again. So you see there is something in some difference in block 3 4 5 and 6 7 8, and you again go and check the table, and you know, okay, the last one is the one creating the issue. So you go there and see, okay, this is the block, but you don't know which qubit in this block. So for this point, you don't even need to worry. What you can see here is this. Let me create something and then try to explain. If I have encoded a bit here, wait a second. Let me ask for 3 qubits. Then. So yeah, all right. Let me take just pi by 4 as some random state. I can take anything else if I want to, but yeah, pi by 4. So putting up a Z gate here, it doesn't make a difference if I put Z gate here or here. So yeah, it doesn't matter where Z gate is, and hence you know if there is an error in this block. So if even if you want to correct it, you can put Z gate anywhere of in these 3 qubit, it will correct itself. So yes, so this part will tell you, okay, error is here, and once that is done, you can basically run this circuit and find out where it is error without disturbing Shaw's encoding and using it repetitively. But yep, why there is not something like that for Shaw's encoding? Why someone has not repeated lead and Shaw's encoding? Because NIST quantum computer doesn't allow you to have these many C naughts you see here. But it does allow you to do something for some simple examples like the ones I have used here and here. And you can see this whole repetition encoding has gone up to 15 qubit repetition code in this paper if you want to. And yeah, if you want to read more about what these operations are, basically what are stabilizers code, you can read thesis of Professor Dr. Daniel Gottesman. It's also here. yes. Other than this, I will just say if you want to do something extra or for fun, you can create a table for source encoding, a similar table like this one. If you want to, as an extra exercise, it will help you. And yes, so that's it from my side as a tutorial. Thank you. And if you have any question, please ask.
Yeah, thank you very much for the session. Any questions, anyone? Right now is a good time to ask. Okay, I guess there's no questions. So before we leave, you can find the links in the chat box. We'll also share these links in the Slack channel after a while. So I'd like to take this opportunity to thank the members of IndiQ community for taking the time out to help us with this workshop and to provide these demonstrations of Qiskit. Uh, so
Thank you, Praveen. Thank
I
you for having
guess
us here.
yes,
It's been a pleasure.
yeah.
Thanks, Praveen.
Thank you, Praveen. Yeah.
I hope everyone enjoyed the session, and we'll be continuing tomorrow. So if you have any questions about both Qiskit and any other material covered today, you can ask the Slack channel, and we'll be happy to help. And so tomorrow, the session starts at 9 o'clock, and 9 o'clock we'll just have a tutorial session where if you have any doubts on the problem sets, we'll just take it. It'll be completely open for questions. And if you have any questions about Qiskit also, we'll be happy to help. We won't be solving any problems as such. We'll just be taking questions. So after that, tomorrow's first lecture will be at 11 o'clock, followed by the fifth lecture of the series, which will be at 2 o'clock in the afternoon. The public talk will be at 4 o'clock and will last for 1 hour. And I hope all of you have registered for it. If not, we'll be sharing the meeting link in the Slack channel anyways. So you can let your friends know about the public talk and they can attend. So thank you all for attending today's lectures and tutorials. I'll see you tomorrow. See you guys.